So 5.6, modeling harmonic motion. This is our last section of chapter 5. This also means this is your last day of notes for the 2025 year. No more notes until 2026. Okay, so when we're modeling harmonic motion, we can use sine and cosine because they have periodic behavior. Okay, so the harmonic motion is going to be modeled with sine and cosine graphs. We're going to look at the graph of sine and the motion of a vibrating spring that follows the sine below. And one thing we're going to look at in that graph is how the mass returns to its original position. It does that over and over again because it's a cycle. Okay, so a cycle is going to be one complete vibration of an object. And then we're going to be using some equations that are going to be very similar to what we're already using. There's just going to be one small difference. All right, so we are going to look at the spring in figures 1 and 2. Okay, so here you have your sine curve, and then this is showing you how the spring follows that curve. Okay, so this is the original position at 0. And then notice it returns to that original position here and here. Okay, so the string is being stretched and compressed. Okay, so in simple harmonic motion, we have the equation y equals a times the sine, and this is like a fancy W. Okay, it is actually the lowercase omega. Okay, you guys are probably used to seeing the uppercase omega. So if you look at that equation, you can see it's identical to what we've done before. It's just now we have omega instead of the value of k. And instead of the input being x, it's going to be t, because we're going to be looking at what happens over time. All right, and then in this case, your amplitude is going to be the absolute value of a. The period, instead of 2 pi over k, is going to be 2 pi over omega. And your frequency is going to be omega over 2 pi. So it is the reciprocal of the period. So you can use that to help you if you have to find both. So if you have to find the period and the frequency, once you find the period, you can just use the reciprocal. Okay, so the main difference between these two equations is going to be the starting point. So when the value of t is 0, we're going to calculate what happens with both sine and cosine. All right, so we're going to start with sine. So if t is 0, y equals a times the sine of omega times 0. So if we're calculating that, we know omega times 0 is 0. when you're thinking about what the sign is at 0, just remember you can use your unit circle. Okay, at 0, which is right here, your point is 1, 0. So is the sign going to be your X or your Y? Your Y. So it'll be 0. Okay, so this is going to be A times 0. So in this case, we say that the sign has 0 displacement. Okay, so if it starts at 0, we say it has 0 displacement. So in this first case, the motion starts with the value of 0. Okay, when we look at your cosine, and we plug in 0 for t, we're calculating the cosine of 0. So if we use the point, you can see it's 1. Okay, A times 1 is just going to be A. And remember, A is equivalent to your amplitude. Okay, your amplitude is going to be equivalent to your maximum value as long as there's no vertical shift up or down, which there will not be in this. So the cosine has what we call maximum displacement. And that just means you're going to be starting at the maximum when the value of time is 0. Okay, so in the second case, the maximum starts, or the motion starts with the maximum value. Okay, and those are two of the main things that we're going to focus on today when we are graphing. Now, this picture is great below. You might remember some of that in your opening slide today. So this shows you that you're finding the period. Your period is going to be 1 cycle. Your amplitude is always the distance, half of the distance between the max and the min, and it's always positive. So that's why they're showing that to you as half of the distance, okay, in the positive region. And then everything we're going to do today is going to be a function of time. So your input value is going to be t. Okay, so as a spring like coils and compresses, we're going to show that it follows a periodic cycle of sine or cosine. All right, and then from there, we are going to graph, we're going to find the amplitude and the period and the frequency. So the displacement of a mass suspended by a spring is modeled by the function y equals y equals 1.2 sine of 4.8 t. Okay, I want you to go ahead and write down what your amplitude is going to be. So you write down your A, and you should also know how to find your period. All right, what did you get for your amplitude? 1.2. Okay, so it's just your A value. It's always going to be positive now because it does represent your amplitude. And remember, your period is 2 pi divided by your omega value. All right, so Eli, what's my value of omega for this one? Great. Okay, so if you are plugging in the 4.8, when you have a fraction, you don't want a decimal within your fraction. So how can I convert this so I don't have my decimal anymore? What do I do so I don't have my decimal? What's that? Yeah, multiply by 10 over 10. So you have to multiply by a value that's equivalent to 1. If you multiply by 10, it just moves your decimal one place, right? So that becomes 48. This becomes 20. And then you can reduce however you want. Some of you might notice right away, hey, 4 goes into both. Some of you might say, oh, I can cut that in half. Okay, whichever one you want to use is fine. Okay, but if you divide by 4, you get 5 pi over 12. Okay, that's going to be your period. Okay, and we are going to be using that to graph. Now, earlier we talked about when you have the frequency, it is the reciprocal of the period, so 1 over p. So if p is 5 pi over 12, that just means your frequency is what? 12 over 5 pi. Okay, so you can just flip it. Could you plug it in and do it that way? Yeah, you definitely could do that as well. Okay, but you have to simplify again, so I would just use the reciprocal. All right, now when you're sketching the graph in this section, there's a few things we have to be mindful of. So remember that your x-axis is now t. So when we are sketching with time, you only have to graph your positive values. Which means we will not be using the negative side of your x-axis, which is the time. Okay, and then when you have sine, that's going to be 0 displacement. That really isn't new for you because you know that sine starts at 0. So that would be something you would already do. At 0 for sine, you're going to start at 0. Also, just like we did earlier in this unit, you're going to start at 0. You're going to end where? Where's your ending value? It's 5 pi over 12 because that's the what? Period. Okay, so you're going to end at your period where you're also 0. Now, to find the halfway mark, okay, halfway is just cutting this in half, which is multiplying by 1 over 2. So if I multiply 12 by 2, I get 24. So I have 5 pi over 24. Okay, so when we graph this, we're gonna do one period, so we're gonna end at 5 pi over 12. You might remember me saying when we started sine and cosine, a good scale would be to divide your period by 4. If it's a fraction, you just multiply by 1/4. So what's 12 times 4? 48. Okay, it's the same thing as cutting this in half. Half of 5 pi over 24, multiply by a half, you get 5 pi over 48. Okay, go ahead and find this third value and fill in your y. And I'll come around and see if that's something that we can help with or something that we know how to do without me. Okay, so in the middle we have 0. Remember here we're going to hit the maximum unless there's a reflection. So your maximum is your amplitude, so you should have 1.2, negative 1.2. Looks like we're pretty comfortable with that. If you're having trouble with figuring out what this is, remember that you just set the scale at 5 pi over 48. So 5 pi over 48 is what you're counting by. So if you add another 5 pi over 48, that's when you get 10 pi. 5 plus 5 is 10. And that, of course, is going to reduce. So if you divide by 2, you get 5 pi over 24. Okay, do you see how we already have that on our graph? So if you want to find the next one, I'm actually going to add it to this because you have the common denominator. You just add 5 pi over 48 to that. 10 plus 5 is 15. Okay, 15 pi over 48 is going to be that third location. And if you were to add the 5 pi over 48 again, of course you would get the 20 pi over 48, which does reduce to 5 pi over 12, which you already have on your graph. So once you find what you're going by, you just keep adding that to find your value. Okay? So now we're going to graph this. So we're going to start at 0, 0. When you are scaling, make your scale something simple. So if it's 1.2, I decided to go by 0.6, because if this was 0.6, this would be 1.2. That means this would be negative 1.2. So I'm going to start at 0. I'm going to end at 0. Halfway is 0. Halfway in between there, I reach my max. Halfway between, I reach my min. And then I'm going to be connecting with a curve. Okay, and you are going to put an arrow on that right side because it is going to continue as time goes on. Okay, for example 2, we're going to repeat parts A and B from example 1, but we're going to have a new equation. That new equation is y equals negative 4 times the cosine of t divided by 2. So negative 4 cosine, and that is t divided by 2. Okay, so your amplitude, Logan, what's our amplitude going to be for this one? 4, good. So even though it starts with a negative, our amplitude is still positive. Okay, and then Ali, what's my omega going to be for this? What am I going to plug in here? 1/2. So when you do 2 pi divided by 1/2, it's really just like you're doing 2 pi times what? 2, so you're going to get 4 pi as your period. Okay, and then just like we did before, your frequency is the reciprocal. So if you have 4 pi, your frequency is just 1 over 4 pi. Now the frequency isn't something that you need to create the graph, but it is helpful to understand what it means. So the frequency means that you have 1 wave every 4 pi. Okay, for this one, it means you have 12 waves every 5 pi. So if we were to continue this graph out to 5 pi, we would see 12 cycles. Okay, that's what the frequency is. All right, so then let's create our graph. So for cosine at 0, normally you're at your max, but because of this negative, you have a reflection. Okay, so think about what that does to your scale. So normally we have 0 and 4 pi. We start at the max. Instead, we're going to start at the min. Okay, and it's because it's a reflection. If you didn't have a reflection, you would start at the max. Okay, halfway in between, that's when we're going to reach our max now. Halfway between 0 and 2 pi is pi. So now we count by pi. 1 pi, 2 pi, 3 pi. Okay, zeros in between. All right, so a lot of this should feel like review in terms of your graph. Okay, you have t, your time, so we aren't going to continue into the negative. 1, 2, 3, 4, so I have negative 4 here. And then I'm going to also end my period at negative 4. At 2 pi, I'm at 4. And then halfway, I'm at 0. Okay, do not connect these with a straight line. If you need some help with the shape, I recommend connecting these 3 together first. Keep in mind that this would be a curve. And then you would be going to this point here. Okay, so this is also going to be a curve. Okay, so cosine is normally your maximum displacement, but because of the reflection, it now starts at your minimum. All right, and then aside from graphing, we are going to be finding functions today. Okay, so for both example 3 and 4, we are finding functions that model simple harmonic motion. So in example 3, models simple harmonic motion. Example 4, models simple harmonic motion. And in both of these, you are given an amplitude. Okay, and then in example 3, you are given the period. Example 4, you are given the frequency. Okay, and then one of them is going to assume the displacement is at 0 at the time t is 0, and the other one assumes it's at its maximum. Okay, so I want you to think for a minute about why they tell you that last thing and why you need that in order to find your equation. Okay, so when they tell you that the displacement is 0, what does that mean about your function? Yeah, it's going to be a sine function. Okay, so if it is 0, then you have to use a times the sine of omega t. And the only things we need to make the function are a and omega. If it's the maximum, it's going to be cosine. And again, you need a and omega. Well, they already give you the amplitude in both of them. So the amplitude here is 10. Our amplitude for this one is 6.25. We have to find omega. So in example 3, we are given the period, so that's what we're going to use. Okay, so use the period. To find omega. So I want you to give that a try. So think about how you're going to use your period to find your omega. Okay, so if you're having trouble getting started, let's think about what our equation is to find the period. So the period is 2 pi over omega. And if you know your period is 3, you can just substitute 3 in, and then you can solve. Remember, if your variable's in the denominator, you are going to have to multiply by that value to simplify. Okay, so you have omega times 3 equals 2 pi. So to get omega by itself, you would just divide. Okay, so that is what we're going to substitute into our equation. Okay, so our final answer is y equals 10 sine of 2 pi over 3t. Don't forget the t, because a lot of times we do all that work to find the 2 pi over 3. Sometimes we forget the input, okay, but you have to make sure that you also include your t in there. Okay, so using that, see if you can use that to help you to find omega here. So now we're going to use the frequency. Okay, use the frequency to find omega. Use are probably used to seeing that omega. Omega is flexing. Or an octopus. Usually not bad. All right, so let's. Okay, and then when you solve here, okay, your frequency is omega over 2 pi. So remember, that's one of the things we wrote down. So if your frequency is 60, omega over 2 pi, okay, you're going to multiply both sides by the denominator. So omega will be 120 pi. Okay, so then your final answer will be y equals 6.25 cosine of 120 pi t. And again, just make sure you put that variable in there. So you need your input variable t, you need your output of y. Okay, so all of that is simple harmonic motion, and it acts just like our sine and our cosine graphs. Now we're going to talk about what is called damped harmonic motion. Okay, so the spring that we talked about on page 1, that is assumed to oscillate in a frictionless environment. In that case, the amplitude will not change. It's always going to reach the amplitude. Okay, and that is called simple harmonic motion. In the presence of friction, though, which we do live in a world with friction, the motion of that spring eventually dies down. So I like to think of this in terms of furniture. Okay, maybe you guys are like me, and do you have like a favorite spot on a couch? Like you always want to sit in that spot? Or maybe one of your family members does, like you know that's their spot. Eventually, when you keep sitting down in the same spot, what happens to that space? When your grandpa's been sitting in the same chair for 20 years, over time, what happens? Yeah, there's an index, right? It's because the spring dies down, right? It can only go back and forth so many times, and then because of that friction, because of that pressure on there, right, it's going to die down. So that is going to decrease with time. That's why we buy new furniture, right? Okay, so the amplitude decreases with time, and that is called damped harmonic motion. Okay, it's because it dampens. Okay, it dies down. Okay, so this equation looks more complicated. This is not an equation you'll have to have memorized, but you are going to see our good buddy E comes back in the game here. Okay, so it's KE to the power of negative CT multiplied by the sine of omega t, or you can have that same value but with the cosine. Okay, and then they tell you what all of your variables stand for here. So it's damped harmonic motion. The constant C is called the damping constant. K is the initial amplitude. And they call it the initial because it's going to decrease over time. And then 2 pi over omega is still going to be the period. Just know that a period is going to be still your cycle. You just aren't always going to be at the same place like in our frictionless environment. Okay, so we're going to draw a pair of graphs below together. One is going to model harmonic motion, and the other is going to model damped harmonic motion. And in the first one, we're going to draw one where the A value is 4, and we have maximum displacement. But I'm going to guide you through that. And then with this one, we're going to have K is 4. And again, we're going to be at the maximum displacement. Now with some of the graphs, it takes a long time for you to see how it decreases. Like sometimes it decreases gradually. And so we want to look at a bigger picture to see what happens over time. So for these, I'm going to let you do an exaggerated model, okay? For the first one, we're going to do simple harmonic motion. And when you have simple harmonic motion, okay, it always reaches the amplitude. All right, so we're going to start with an amplitude at 4. And then I'm going to make your period 1, 2, 3, 4 units. So it's going to end at 4. And then halfway, 1, 2, 3, negative 4. And I'm just going to label the 4 and the negative 4. And then halfway in between, you would reach 0. Okay, and then we're going to repeat that. So we have 0, negative 4, 0, positive 4. And this is going here. Okay, and that's because I want you to see more than one cycle. Okay, so in simple harmonic motion, you are always going to reach.
Please pardon the interruption, but at this time, teachers, please release all bowlers.
Okay, so if it's simple harmonic motion, it's always going to reach your amplitude. Okay, for damped harmonic motion, the amplitude decreases over time. Okay, so for this one, we're going to start at 1, 2, 3, 4. And then, like I said earlier, I'm going to let you draw an exaggerated version. So I'll just have you watch me and then I'll give you time to do it. So because it decreases over time, I'm going to let you just start at the maximum. And then you're just going to show that over time, it gets smaller and smaller. Okay, and then you can just do that all the way to the end. Okay, so we're going to do an accelerated graph where you can see it's dampening over time. And for that reason, I'm not going to make you label your x values, because the main thing I want you to see for this graph is that the amplitude is decreasing over time and what your starting value is. Okay, and why does this decrease over time? Due to what? So yeah, why does this decrease? Due to what? Due to friction. Okay, so that's something that we have to know. All right, so in our last example, it tells you that you're given an initial amplitude, a damping constant, the frequency, or the period. And you'll see the directions they look exactly like this, where they remind you that frequency is 1 over the period. And it says, first, find a function that models the damped harmonic motion, and then we're going to graph the function. We're going to use a function of the form y equals ke to the negative ct cosine of omega t. So right in the equation, right in the directions, they're going to give you the equation. That's why you are not going to need to have this memorized. Okay, the form will be in the equation. Okay, and for part B, we're going to use sine. Okay, so part A is cosine. Part B is going to be sine. Okay, and then we're going to graph those. So for part A, we have K is 100, C is 0.05, and the period is 4. So we're given the value of K, we're given the value of C. What we don't have again is that omega, so that's what we're going to find. Okay, so to find omega, just like we did earlier, we're going to use the period. Okay, so the period equals 2 pi over omega. All we have to do is substitute in our value. And last time I showed you how you could multiply by the denominator. Don't forget that you can also cross multiply. That's an option. So if you wanted to put the 4 over 1, you have 4 times omega, which would be equal to 2 pi times 1, or 2 pi, and you could solve that way. So when you reduce, you'd have pi over 2. Okay, so then your equation would be y equals 100e to the negative c. I will, thank you. Okay, and then this would be the cosine of pi over 2t. Oh, and then you also need your t here. All right, and then I'm going to give you this part, and I want you to do the equation, and then we're going to do the graph together. Okay, so when you found omega for this, remember your frequency is just omega over 2 pi. So if you have 20 equals omega over 2 pi, all you have to do is multiply those together. So 2 times 20 would be 40 pi. And now you can plug that into your equation. So y equals 0.3 e negative 0.2t cosine of 40 pi t. All right, and then from there, we're going to do our graphs. So this is what I'm going to be looking for on your graphs. If you have your cosine, you have to show that it starts at your maximum, which is going to be your initial amplitude, and that is your K value. Okay, so when you graph that, again, just make this an easy scale. So like you could do 20, you could do 50. So I did 20, 40, 60, 80, 100. And then you can just label those so you know what your scale is. Okay, and then you are going to start at the maximum. So your maximum would be 100. And then when you draw this, The main thing is it only reaches your amplitude once and then it decreases over time. Okay, and so we're just going to show it decreasing. And like I said, this is an exaggeration, so it's fine if yours doesn't look exactly like somebody next to you. The main thing is you have the maximum displacement. It's not going to hit the 100 or negative 100 again. Okay, now when you do the sine, the key points there is that it starts at 0. And whatever your K value is, if your K value is 0.3, you have to make sure when you're graphing, it will not go above 0.3 or below negative 0.3. Sometimes people just get too excited when they're doing the exaggeration. They start like making big waves, okay? But you have to make sure that it's between that original amplitude. So if I have 0.3, I think a good scale would be to go by 0.1. So if you have 0.3 and negative 0.3, this is sine. So we're going to start at 0. And then one thing I do to help me from going below is I'll just put my hand there so I can. So it can reach your amplitude once, and then it will not reach it again. So over time, it's just going to get smaller and smaller. And we're not labeling the T because we are showing what happens after an extended period of time. Okay, so the main thing is that you know that it's going to die down due to the presence of what? Why does it die down for the damped harmonic motion? Friction. Okay?